Alright, the goal of this video is to show you how to do some more precise math with vectors, something that's going to give you a better answer than adding things tip to tail. And to do that, we're going to use an example. Suppose you have a military drone flying at 200 miles an hour, and there's a crosswind. So there's a wind that's blowing, but not exactly crosswise. It's blowing at 100 miles an hour. This thing's way up in the air. 100 miles an hour at an angle 60 degrees to the direction that the drone is traveling. How fast is the drone going, and in what direction? It's not going the direction it's trying to go. It's being pushed sideways and forward by the wind. So let's take a look at that. We'll put it on paper and we'll see what things look like, and we'll do this as an example, and hopefully through that you will be able to then solve these types of problems yourself using this as a reference for those new questions. Alright? Let's do it.
Okay, forget the drone for just a second. Any vector can be broken down into a right triangle using sine and cosine. Looking at this one here, we can use cosine equals adjacent over hypotenuse and sine equals opposite over hypotenuse to solve for both the adjacent and the opposite side. If we call this vector A, then we get ax equals a cosine theta and ay equals a sine theta, which are on the Regents reference tables, but not the AP reference tables. Okay, so now that we know that we can decompose any vector into its x and y components by treating it like the hypotenuse of a right triangle, let's apply that to our drone. So our drone is moving along at 200 miles an hour, and then we have this 100 mile an hour crosswind at 60 degrees to its direction of travel. Let's call the direction it's going x and the other direction y. Alright, so let's look at this crosswind by itself. We have an x component and we have a y component. The x component, we're going to use ax equals a cosine theta. We're going to plug in our numbers and get 50 miles an hour. For our y component, we're going to plug in and we're going to get 86.6 miles per hour. And these are going to make up the component vectors of our crosswind velocity vector. So these components are separated into the x and y components, and for some reason physicists have decided to use these little unit vectors. Instead of calling them x and y and z, they decided to call them I hat, j hat, and k hat. So I is x, j is y, and k is z. We're never going to use the z direction in this class, so don't worry about it. So we have an I hat and a j hat. We have 50 I hat and 86.6 j hat. 50 I hat plus 86.6 j hat equals the crosswind velocity vector. And this is how you write down vector components on a piece of paper dealing with two dimensions. Now that you have those two dimensions, you've got your velocity vectors for both the drone and the crosswind. The drone is 200 I hat plus 0 j hat. The crosswind is 50 I hat plus 86.6 j hat. Just add the I hats together and add the j hats together. In other words, add the x components together, add the y components together. 50 plus 200 is 250. 86.6 plus 0 is 86.6. So the resultant vector is 250 I hat plus 86.6 j hat. And those components look like this. Your I hat is the black vector and your j hat is the gray vector. We can now take those vectors and add them tip to tail. We can take the gray vector, move it over to the right, and add them together to get our resultant. That resultant is the same thing as 250 I hat plus 86.6 j hat. The magnitude of that resultant you can get because it's a right triangle. Use the Pythagorean theorem, and the magnitude, we use absolute value signs to represent that, is the square root of 250 squared plus 86.6 squared, which is 265 miles per hour. And so this thing is going 265 miles an hour, and we just need a little bit more trig to get the angle. That angle we can use arc tangent. You can really use arc, sine, cosine, or tangent here because we know all three sides of the triangle. So I used arc tangent here of opposite over adjacent, 86.6 over 250. The arc tangent of that number is 19.1 degrees, and that is our answer.
And that is how you do it. You take your vectors, break them down using sine and cosine into perpendicular components. Add those perpendicular components together individually. Add all the x components, add all the y components. That gives you your x component of your resultant and your y component of your resultant, which you can then combine back together using the Pythagorean theorem in order to get your final answer. That hypotenuse magnitude is the magnitude of your resultant. And then you use trig, arc, sine, cosine, or tangent in order to get the angle. If you can follow through that problem, then you can solve any combination of vectors. That is as much as any of you need to do. I will do one more video giving an example of what if you have 3 vectors that are combined together. And that'll be the next video. Regents, you can ignore that completely, but AP, you'll want to pay attention to that one. All right? Great.